Welcome to a lesson on integrating the 6 basic trigonometric functions. So in the previous video we discussed these integration formulas, and these were based upon the derivative of the 6 basic trig functions. However, you can see that these integration formulas are missing 4 of the basic trig functions. We have sine x and cosine x, but these other 4 are just special forms of the remaining trig functions. But what we're going to do now is use the log rule for integration, as we see here, to come up with all of the integration formulas for the 6 basic trig functions. So let's take a look at them first. These first 2 are review. We've already covered these. And now notice on the next 4, we start to see the natural log function occur. And so what we're going to do is take a look at a couple of these and see where these integration formulas come from, and then we'll do some examples. Let's start by taking a look at the integration formula for tangent u. Let's see if we can come up with this integration formula by taking a look at the integral of tangent x with respect to x. Well, we know that tangent x is equal to sine x divided by cosine x. Now, if we perform u substitution and let u equal cosine x, du would equal negative sine x dx. Notice that our integrand does contain sine x dx. So what I like to do is solve this equation for sine x dx. So we'll divide both sides by -1. So we end up with negative du is equal to sine x dx. So we can replace sine x dx with negative du, and we can replace cosine x with u. So let's go ahead and rewrite this in terms of u. We'd have negative 1 over u du. And we know the antiderivative of 1 over u is equal to natural log u, so we have negative natural log u plus c, but we want our antiderivative in terms of x, and we know that u is equal to cosine x. So you can see that what we found matches our formula, except this is written in terms of u because we may have to perform substitution to make it match this form. Let's go and take a look at this integration formula. This one's a little more involved. Let's see if we can come up with it. Let's take a look at the indefinite integral of secant x. Let's put secant x over 1, and we're going to multiply the numerator and denominator by secant x plus tangent x. So let's go ahead and multiply this out. We'd have secant squared x plus secant x tan x all over secant x tan x. Now we can apply that same technique. If we let the denominator equal u, this works out really nice because the derivative of secant x is equal to secant x tangent x, and the derivative of tangent x is equal to secant squared x. Now you'll notice this matches our numerator perfectly, so we can replace all of this with du, and this would be 1 over u. So we can rewrite this as 1 over u du. And we know how to integrate this. This would just be natural log absolute value of u plus c. But of course we want our antiderivative in terms of x, so we have natural log of secant x plus tangent x, which again matches the integration formula that we were given, except this is written in terms of u again. Let's go and take a look at some examples using the new integration formulas. Again, I put them over here on the right side for reference, but you should memorize them. So right away we can see that this formula here is going to help us, but we do have to perform u substitution, where u would be equal to 5x, so du would equal 5 dx. Notice right now we don't have a 5 dx in our integrand, we have a 2 dx. So let's go ahead and solve this for dx. We'll divide both sides by 5. So this means that 1/5 du is equal to dx. Let's go ahead and do the substitution now. Notice we have not accommodated for this 2, so that's going to stay there. This is equal to 2 times, now dx is equal to 1/5 du. So we'll have 1/5 du, and then sine 5x is just sine u. Let's go ahead and rewrite this one more time. This would be 2/5 sine u du. So we'd have 2/5 times, the integral of sine u is negative cosine u, so we'll have negative cosine 5x plus c. Let's go ahead and try another one. Here we have the indefinite integral of x squared cotangent x cubed. Since we've already covered basic u substitution, if we let u equal x cubed, then du will equal 3x squared dx. Notice we have x squared dx. Let's go ahead and divide by 3 so we can say that 1/3 du is equal to x squared dx. So x squared dx is the same as 1/3 du, and x cubed is now just u. Let's go ahead and rewrite this. We'd have 1/3 du and then just cotangent u. Of course, this fits one of our new integration formulas. This antiderivative will be 1/3 natural log sine u. Of course, u is equal to x cubed plus c. Now we have a definite integral. Now this one we do have to remember one of our identities. 1 minus secant squared x is equal to tangent squared x. And the square root of tangent squared x would just be tangent x. Now if we take a look at our integration formulas, this will equal negative natural log cosine u. So we have the antiderivative equal to negative natural log absolute value of cosine x. Now remember, this is a definite integral, so we do have to evaluate the antiderivative at the upper and lower limits. So we'll have negative natural log absolute value of cosine pi over 4 minus negative natural log absolute value of cosine 0. Well, cosine of pi over 4 is square root 2 over 2, so we have negative natural log square root 2 over 2. This would be plus the natural log of cosine 0, that's equal to 1. Well, natural log 1 is equal to 0. So we have negative natural log square root 2 over 2. And if we wanted to, we could rewrite this as negative natural log square root 2 minus natural log 2. Let's go ahead and check this one on the graphing calculator. Let's first convert this to a decimal. Now let's go ahead and compare this to the definite integral on the calculator. We press math, option 9. Let's go ahead and type in the integral in this form. So we have tangent x comma x comma the lower limit comma the upper limit. So 0 comma pi divided by 4. Now you want to make sure you're in radian mode. I've already checked that. And you can see it matches nicely. So our work checks. Hope you found this video helpful.